Hello, good morning to all of you. So today I'm going to discuss about the ab initio methods. So if you follow our lecture from the past, at the first we have discussed about the introduction to computational chemistry, and then we have discussed that what are the properties we can compute, and after that we reached to the sections where we are discussing about that what are the fundamental principles behind all these computations. So in last two lectures I have discussed about molecular mechanics method, and you remember that this in this method we assume the molecule as a ball and spring model. So it has so many advantages and disadvantages also, uh, and that were also discussed that as it's the calculation is very fast, so you can use molecular mechanics method to compute the properties of protein, DNA, like big molecules. But it has also a severe drawback that it does not consider any electronic distributions, or it does not at all consider the electron density phenomena. So it cannot actually explain the reaction mechanism or any type of chemical reactions, because you know that chemistry is nothing but the bond breaking and bond making process. So as molecular mechanics cannot explain any bond breaking or bond making process, so we have to shift another method if we want to consider the electronic influence in the molecular reactivity or in the reactions. Then we have to move to the other method from the molecular mechanics. So what we have to do, we have to basically solve the Schrodinger equations, because Schrodinger equation consider the electronic phenomena. So let's start the most initial methods, that is the ab initio method. And ab initio methods is actually the name comes from the Latin, that is called from the beginning, means that it actually do the computations and that derived from the direct theoretical principles with no inclusion of experimental data. Like in last class also you have seen that in molecular mechanics we have parameterized the things that like from like the value of the bond strengths, uh, constants of the force constants, we have all actually taken from the experiments. But in ab initio method, only from the theoretical principles, no experimental data will be included here. So this is nothing but basically what we do. This method is just to solve the Schrodinger equation approximately, because we cannot solve it exactly. Okay. So what are the type of mathematical approximations we can take? So this is just a method. We can take the simpler functional form for a function of finding approximate solution to a differential equations. Okay. So there can be any type of form that we will discuss one by one. So here one important concerns of that Schrodinger equations actually is very easy to write for any collections of nuclei and electrons. You have also seen in quantum chemistry class that we actually can write Schrodinger equations for any type of molecules. But the problem is that it cannot be solved except for the hydrogen atom. Okay. So what actually the things are here, that we know we can define the system, but we cannot actually get the exact value because we cannot solve the equations. Okay. So for that, this situations is careful, very described by P.M. Dirac in a very well quote, that he said that underlying physical laws necessary for the mathematical theory of a large part of physics and the whole part of chemistry are thus completely known. Means that you can define all the part. But the difficulty is only that the exact application of these laws leads to equations much too complicated to be solvable. So for that, again I am telling you that what we will calculate this, that will not be exact value, that all are approximate value. So we can say that we can predict the properties of molecule using the ab initio method. So let's discuss about the approximations. So first approximations will come. So before the approximations, you should know about the Schrodinger equations for multi-electron, multi-nuclear systems. That is simply we write H psi is equal to E psi, where H is the Hamiltonian, psi is the n electron wave function, and E is the energy. When we actually solve this equation, we will get the energy and the wave function back. Okay. So what are the form of Hamiltonian? For a multi-nuclear multi-electron systems, you know Hamiltonian is just contains two terms, that's kinetic energy and potential energy. Okay, so kinetic energy here the first two is the first part is the electronic kinetic part, second part is that nuclear kinetic energy, and then the potential energy contributions that is coming from electron nuclear attraction term and electron repulsion term and nuclear repulsion term. So these were discussed carefully, I think, in quantum chemistry class. You should go back again in the literature and you look for this. But again, I need to recollect this, so I am just going to discuss that all the symbols are used here as general symbols, like E for electrons, electronic charge, ZA for the nuclear charge, where R is the distance. Okay, and m is the mass of the electron, ma is the mass of nucleus. Okay, so next the first approximations we should take to solve the Schrodinger equations, that is the Born-Oppenheimer approximation. Okay, and these approximations, the main idea of these approximations, that our assumption is that electrons are moving extremely fast compared to the nucleus. Okay, so you can assume that the nucleus are stationary with respect to the electrons. So here we can ignore two terms. One is that the kinetic energy of the nucleus, this term, the second term, and also this term is actually constant, because we are assuming that nucleus are in the fixed positions. So what we can do, we can solve the other terms and we can just add this term with the later. Okay, so as this is constant, this will not change the value of the other part. Okay, so basically when we actually incorporate the Born-Oppenheimer approximations, what we'll get the Schrodinger equations for electrons. That is called electronic Schrodinger equations, and we can write that H EL is equal to psi EL, EL and psi EL. Okay, where H electron, the Hamiltonian of the electrons are where electronic kinetic energy you should consider, and electron nucleus attraction, and also electrons repulsion. Okay, so here one concern is that in this electronic Schrodinger equations, the mass of the nucleus are not coming. So to the extent that the Born-Oppenheimer approximation is valid, this means that kinetic isotope effect on molecular properties, you know that kinetic isotope effect in physical organic chemistry class maybe. So there must be some different origin for the isotope effect, because in the Schrodinger equations we do not have here nuclear mass, so we cannot actually, otherwise we cannot calculate this. Okay, so the nuclear Coulomb energy, the last term equation 2, we have to add after solving these equations. Okay, so finally we will get then total energy. So now this Schrodinger equations in SI unit looks very complicated, because you have so many terms, that Z, E, 4 pi, epsilon 0, so many terms are there. So what we can do, so in these equations, these are all in SI unit, like a mass in kilogram, electron in coulombs, R1, R2, R1, 2, these are all in meters, etc. Okay, so what we can actually simplify here, that we can take all the values, like the Hamiltonians, whatever all these values Hamiltonian possesses. So let's we can assume that, let's say take H cross is equal to 1, mass of the electron is 1. Okay, and mass of the electron 1, charge of the electron 1, and if we take all this unity, then what we'll get, this 4 pi epsilon 0 is 1, z is 1, z can be there because z is the nuclear charge. So here we'll get now all h, m, e term will be not there. So we'll get a very simplified form, that is just from here half will survive, half and del 1 square del plus del 2 square. This is we have wrote for helium atom, so it's the kinetic energy of electron 1, this is kinetic energy of electron 2, then minus z by r1 means that this is the nuclear attractions of electron nuclear with electron 1, and this is the attraction of nucleus with electron 2, and this is the electron repulsion. Okay, so this looks very simple with the in context of these equations, which is written in the SI unit. Okay, so now if we solve these equations now in atomic unit, then what will be the energy unit here? Because here as it is the SI unit, if you solve in this form, you will get energy in joule, because that is the SI unit of energy. But here what will be the unit you will get if we assume that all these things are unity? So that let's discuss here for now. So using atomic units, it simplifies the quantum mechanical expressions very much. Okay, and the results are calculations are independent of the currently accepted values of physical constant in terms of coulombs, meters, or kilogram and seconds. Okay, so if you solve, we can get the atomic unit of a quantity by combining all this term to give the expressions of the required dimension. If you put all this on the dimension, then atomic units of length and energy will be in the Bohr and in the Hartree. Okay, so 1 Bohr is, you know, A0 is equal to 4 pi epsilon 0 by this form, and this is this is semicolon is given, this is 0.0529 nanometer, where 0.59 angstrom, and energy will be in 1 Hartree, because it will come as a Hartree unit, and this actually, if you transform this to the joule, kilojoule, then you will get this 2625.5 kilojoule per mole inverse. Okay, so actually when you do the computation using a program in lab class, what we will get the energy in this unit, in Hartree unit, or length in Bohr unit. So if you want to compare, because this is a very high value unit, you have to compare this, you have to convert this energy unit to the kilojoule unit for our discussion. Okay, so as here written, 1 Hartree per particle is equal to 2625.5 kilojoule mole inverse, so you can assume that this is a very big value. Okay, so the Bohr of the radius of a hydrogen atom is in the Bohr model, or the most probable distance of the electron from nucleus to in the Fourier-Schrödinger picture, because we can not also always assume that, we cannot assume that electrons are like particle according to Bohr model. Okay, so the Hartree is the energy needed to move a stationary electron 1 Bohr distance from a proton away to infinity. If you define that, the energy of hydrogen atom relative to infinite proton electron separation is as 0 is minus half Hartree, the potential energy is minus 1 Hartree, and the kinetic energy is always positive, that is plus half. Okay, so Schrödinger equations are atomic unit. Let discuss little more about that. So here we have shown in a pictorial representations. So here two nucleus are two protons are there, so two positive charges are showing, and the electron 1 and electron 2. So first two terms is the kinetic energy of electron 1, this is kinetic energy of electron 2, and you can see this using by this arrow, which is showing opposite to each other, that is attractive term, that is minus z by r1, this is minus z by r2, and here is one arrow is showing diverging, which is actually showing your electron repulsion term. Okay, so one concerns is that in this helium Schrödinger equations, still we are not considering any effect of magnetic interactions like spin orbit coupling or the relativity. Okay, So basically, in a small smaller atomic number, these two factors are very small or negligible. So we can ignore the relativity or any magnetic interactions for these type the molecules of the periodic table, like 1 2 periodic table in the series in the row of 1 2. So yeah, thank you very much. We'll discuss this in later.